Welcome to part 2 of our lecture video series for Friday, April 21st, where we're going to use the equation that we just derived above for calculating the heat or thermal energy transfer of a particular substance. Let's jump into an example. So to get started, let's look here. All right, so reading through this problem, how much thermal energy? Okay, so first of all, how much something? This question is asking us about thermal energy that needs to be transferred. So this is what we know as heat, right? Heat is the amount of thermal energy transfer as a result of some change in temperature in some quantity of a substance. So how much thermal energy or how much heat needs to be transferred to a 5.5 gram sample of pure water to raise its temperature from 19.5 degrees Celsius to 26.7 degrees Celsius. The specific heat capacity of liquid water is 4.184 joule per gram degree Celsius. I will always give you the specific heat capacities of different substances. However, the one that is for pure liquid water, I highly recommend that you memorize this because we're going to be using it quite a lot. So back to the problem. How much heat? So heat is what we don't know. So let's write out what we do know about heat using our heat equation that includes our specific heat capacity. So Q is equal to M times specific heat capacity C times the change in temperature delta T. Q equals MC delta T. Some students like to remember this using the mnemonic device Q is equal to MCAT because this looks like MCAT. A lot of pre-med students, as you could imagine, really like that acronym. But this is the equation we're going to use, and let's confirm that we have all of the pieces of information needed in order to apply this equation. So let's see here. Specific heat capacity, right? This is what I need in order to relate heat, quantity, and change in temperature. And luckily, I was indeed given the specific heat capacity of my substance. Okay, mass, M. Do I have my quantity of water? So how much thermal energy needs to be transferred to a 5.50 gram? Yes, I do. Sample of water. So I've got this. And I've got this, meaning that what's left for me to find is my delta T, and I am told that I am raising the temperature of my water from 19.5 degrees to 27.6 degrees C. So let's just pull all of this information out of my problem. So M mass is 5.50 grams. C specific heat capacity, C sub S is 4.184 joules per gram degree Celsius. And then delta T, so remember delta is always a change from a final and initial. So final minus initial temperature. So read this language closely. Raise its temperature from 19.5 to 27.6. So this is my 27.6 degrees Celsius as my final temperature. So 27.6 degrees C minus my initial temperature, which is 19.5 degrees C. And let's go ahead and figure out what delta T is now so we don't have to plug it in as a subtraction, right? This difference here in our actual equation. So 27.6 minus 19.5, that gives me 8.1. and that is only 2 sig figs because I'm limited to a decimal in a difference down to the 10th place. So that is 8.1 degrees C. So that is my delta T. And let's now put this together so that we can solve for Q. All right, Q is equal to our mass. So let's just kind of check our units. So, mass. Grams, and if I look at my specific heat capacity, the unit of mass is in grams, so I can leave as is. So that is my 5.50 grams times my specific heat capacity itself, 4.184 joules per gram degree centigrade. So that's grams times degrees Celsius in the denominator. And then let's check that our temperature unit will cancel. So I have my delta T in degrees C. I've also got degrees C in my specific heat capacity, so I'm good to go there. And if I look at my units, I will have grams and then per gram cancel, degree C and per degree C left, or those will cancel, leaving behind the joule unit, which is great because heat is an amount of thermal energy transfer. So anytime I'm calculating an energy unit, this needs to be in joules. We are not biologists in this class. We do not use the calorie unit of energy. So let's go ahead and plug this into our calculators. So 5.50 times my 4.184 times my 8.1 . Okay, I don't think I plugged mine in right, so while you guys are pausing or listening to me struggle with a calculator, you should also be plugging this in yourself. Okay, when I do this, I get, and let's think about our sig figs here. Since this is all products, the total sig figs and the total amount of sig figs as a result of the product is going to be limited to the least precise number here. Here, that's our temperature, which has 2 sig figs. So rounding to 2 sig figs, I'll write the full answer and then I'll round it. 186.3972 joules. So then to 2 sig figs, this would be 190 joules of energy required. So this is how we answer this problem. And of course, let's do a sanity check to make sure that all of our math came out in a way that makes conceptual sense. So let's think about heating, or the sign of Q. So remember, if heat is positive, anytime you see a positive sign in general in thermodynamics, this means that we are absorbing thermal energy, or I guess it's more appropriate to say that thermal energy is transferred to the system. And if the sign on heat is negative, so again, my little way of remembering this, the positive plus, I think of like a hug. It kind of looks like arms that are crossed, right? So bringing in toward the system, positive. And the negative sign is kind of like a little outward arrow, in my opinion. If this helps you, great, use it. If not, then ignore me. But if the sign of heat is negative, then that means that the thermal energy is transferred from or out of the system. So let's make sure, since we got a positive result here in our amount of heat, that this matches kind of what's going on conceptually. So I am trying to raise the temperature of my water, right? So in order to do that, my water needs to absorb energy or have energy pumped into its system. And that means that the sign of Q needs to be positive, which is why this language of required or needs to be transferred to pops up in this kind of calculation. All right, we're going to do another example in the next video. So let's go ahead and split this into 2 examples. And then we'll move on to calculating the total internal energy of a chemical system based on what we know about how to calculate pressure, volume, work, and now heat. And then we'll begin our conversation about enthalpy.